how many ammonia molecules are. Okay, so 1 mole of NH3. It wants to know, A says, how many NH3 molecules? Okay. B says, how many nitrogen atoms? I guess we'll go over here, even though that seems a little bit unnatural. C says, how many hydrogen atoms? And D says, how many total? How many total atoms? Okay. Well, first off, if we have 1 mole of NH3, okay, I know that in 1 mole of NH3, there are 6.02 times 10 to the 23 NH3 molecules. All right, so that's 1 times 6.02 times 10 to the 23 is, of course, 6.02 times 10 to the 23 molecules of NH3. Okay, so if you're looking for how many NH3 molecules are in 1 mole, you just multiply it by Avogadro's number. Now, how about the number of hydrogen atoms? Well, I know that in 1 mole of NH3, okay, there are 6.02 times 10 to the 23 molecules of NH3. Now, in 1 molecule of NH3, how many nitrogen atoms are there? How many? 1. 1 nitrogen atom. Right, because you remember if you draw the Lewis dot structure of ammonia, it looks like this. So this right here is called a molecule, right? Because it has covalent bonds and all of that type thing. And right here there's 1 nitrogen atom in 1 molecule. But how many hydrogen atoms are there? 3. So if we're looking for the number of hydrogen atoms, what do we have to do? Multiply this by what? Okay, 1 mole of NH3. 1 mole of NH3 per 6.02 times 10 to the 23 NH3s. And then in 1 molecule of NH3, there are 3 hydrogen atoms. Okay, so 3 times 6.02 times 10 to the 23 gives me an error. Wait a minute. 3 times 6.02 times 10 to the 23. 1.806 times 10 to the 24 hydrogen atoms. Okay, and of course this right here is 1 times 1, so it is 6.02 times 10 to the 23 nitrogen atoms. Now it wants to know the number of total atoms of all kind. Well, how many total atoms have we got there? 4. So everything's the same except that. So 6.02 times 10 to the 23 times 4 would be 2.408 times 10 to the 24 total atoms. Now you guys do see which number's bigger, 1.806 times 10 to the 24 or 6.02 times 10 to the 23? Which atom's bigger? I mean, which number's bigger?
2.408.
Yeah, that's true. That wasn't a choice, but that's exactly right. Between 6.0 times 10 to the 23, that one and that one's bigger, right? Because remember, with these numbers in scientific notation, you got to look at that exponent as well. Okay. All right, Brittany. How did we do? It is Brittany, right? How do we do?
Good.
Wonderful. Who else got a question? Anybody else got a question? You good with chapter 7? Yes? Wonderful. Well, why don't we start chapter 8 then? What do you think? You going to start chapter 8? Where should we be on the syllabus anyway? Chapter 9? Well, should we really be in chapter 9? Wow. Okay, well we ain't. All right, so we'll do chapter 8 today. We'll pick up chapter 9 next week. All righty. Well, what is chapter 8 about? Well, chapter 8 is about reactions. Now, we know that chemistry, the only way that you know something is going to react is if you actually run the reaction. All right? Now, people will call this place all the time and ask, well, what would happen if you mix these things together? Now, as a chemist, you have to develop some gut intuition about what would happen if you mix these things together. And sometimes nothing will happen, and sometimes, of course, something will happen. So in this chapter here, there are 5 reaction classes that we're going to talk about. Okay? Now, the first one, and the easiest one, I suppose, is something that's called a combustion reaction. Now, combustion means you burn it. Now, most of the time when you burn something, what do you burn it in the presence of? Oxygen, most of the time. Now, you can certainly burn something in a bromine atmosphere or a chlorine atmosphere or something like that. But most of the time when you burn something, it's in the presence of oxygen. So, for an example, if you was to take something like methane, which is CH4, and you burn that in the presence of oxygen. Okay? Now, first off, let me say a word about this. There will always be an O2 on the left-hand side of the chemical equation, and there will always be something that contains carbon and hydrogen only. Now, it does not matter how many carbon it contains or how many hydrogen it contains. Or it contains carbon, hydrogen, and oxygen only. Okay? So there can be no nitrogen here. That would change the byproducts. There would be no sulfur, no bromine, none of this drama. So you always got oxygen, and you've always got carbon and hydrogen or carbon, hydrogen, oxygen. Is everybody cool with that? And when that happens, if you burn something, you will always get CO2 and water. Period. Okay? So it doesn't matter if you burn methane, if you burn propane, if you burn octane, heptane, decane, it does not matter. If it only contains carbon and hydrogen, your byproducts will be CO2 and water. Let me stop for just a minute and define some terms here. First off, everything on the left-hand side of a reaction arrow is considered to be your reactants. Now, sometimes people call these reagents, but whatever, the reactants, reagents, that's what you mix together. So when you burn something, you mix together, of course, methane and oxygen. And everything on the right-hand side here is called the products. Okay? And that is what is formed. In other words, they were not there to start with, or if they were there, then it was not because of this particular reaction. All right? Now, what's about on top and the bottom of that reaction arrow? A lot of times chemists will put stuff on the top and bottom of the reaction arrow like delta. That's probably the most common. And that means for this reaction to happen, you have to heat it. So, if you go over here, you turn on the gas line, it mixes with the oxygen in the room, and there ain't nothing going to happen. You have to do what to it? You have to put heat to it to get the reaction to go. All right. Now, what are some other common symbols since I'm on the topic? Well, another one is something that's called H-nu, and that stands for light. In other words, you have to have light shining on a reaction. If you take the reactions inside of